Okay, so can anybody hear me?
Yes, fine.
I'm sorry for the camera, I tend to move a little too much, but we'll survive. So, but please feel free to stop and ask. This is supposed to be a really understandable talk for every undergraduate, and I think you are already past that stage. So, feel free to know. It should be understandable. If not, I'm making something wrong, so let me know. Okay, so, and I have an excessively ambitious plan. I was going to put okay, I'll move with the arrows. But I have a few topics I wanted to talk besides the excessive large abstract I propose. So let's see what happens. But let me start. When you invited me, I said, well, I have to do something computationally. And a few years ago, I did something that is computationally. It was joint work with my computer and, flesh and blood mathematician. So we start with a surface. This is a pair of pants of a very, very strange person. And here is another version of the pair of pants, flattened. And to study the pair of pants, in fact, to study the curves on the pair of pants, I'm going to cut it up. I want to cut it up without disconnecting it and with cuts that don't intersect each other. So once I cut up, here I draw two possible cuts. They're not the only ones. I cut it, and cuts are labeled. And then I open it up. I'm a topologist, so for me, these two things are the same. And I keep a memory of which piece, which edge, which was glued to which one. And you see it's colored, and there's upper and lower case letters. And that will have a reason. The upper and lower case don't play a role until we have to wait a few minutes to have them play a role. So then one could read, what is the pointer? Here? The other one? I have my own pointer. Can't find it. Oh, here. No? Okay. I have one somewhere.
This one works.
Oh, the other one. Oh, that other one. I was touching at the bottom. Thank you. Okay. So I read. So what I get when I have my polygon opened up, I get a cyclic word, a ring of letters, and I can just copy it here. Here in this case is A, capital A, B, capital B, and then A. Cyclic. I started in some chosen place that I decided in this very moment. And so this is what I get when I cut up a pair of pants. And I'm going to do the same thing with the torus, a little faster. So here it is. The surface word, it was already there. And the surface word we get is A, B, capital A, capital B. And secretly, of course, the capital letters, I use them as an inverse. But, I put this in a computer. I even put a bar in a slide. It's very painful. So capitals are inverse, keeping that in your brain. So here we have two surface words associated to the two simplest surfaces, or the two surfaces with smaller Euler characteristic, which are interesting. These surface words know a lot about the curves on the surfaces. And this is what I'm going to tell you about, what they know about the curves. So now we're going to fix a surface. And therefore, we also fix a surface word. By the way, didn't say very clearly, but there's a choice for the surface words. And for more complicated surface, there might be many surface words, even up to the obvious isomorphisms. But so we're going to fix surface and surface words, and we're going to study the curves on the surface. And these two curves that I have here, the green and the yellow, they are labeled A and B. They are directed curves. The arrow tells you they are directed. And here I have a more complicated curve. And to see what word I'm going to associate to this curve, I start at any point, say here, and I go around, and I'm going to cross. When I cross a label edge, I'm going to record the letter, and I'm just going to record the first letter I see. In this case, it's lowercase a. Every time after I check a lowercase a, I see an uppercase a, but that I'm not going to record because I know that will happen, and we're all smart. We don't need to do redundant things. So this is lowercase a, go around, go around, go around. Lowercase b, go around, go around, go around. capital A, go around, capital B, go around, and then I come back where I started. So this is, again, a ring of letters. It's a different type of rings of letters, but it is a ring of letters associated now to this surface with a fixed surface word. And this ring of letters I just read off, it's a curve word. And these curve words are slightly different. I mean, if I tell you what are the rules that a surface word should follow, you probably can say, you know, they all have finally many letters. Each letter appears in lowercase and uppercase exactly once, and that's it. The curve words that I'm going to choose are reduced, and you probably can guess why. Well, because, you know, for instance, this curve here that, you know, when I start here, I read capital B, go around, and then small b. That's redundant. I can always make my curve tight and eliminate such things, so I can assume that my curve words are reduced. And so this is the curve word, the curve word associated to that class. So here is the protagonist of, for at least the first part of my talk, the free homotopy classes of curves, of closed curves on a surface, closed directed curves on a surface, or deformation class. These are classes up to deformation, no fixed point. The free tells you there's no fixed point. And they are always in one-to-one correspondence with conjugacy class of the fundamental group of the surface. And when your surface has boundary, like the surface we just discussed, this set of free homotopy classes is in one-to-one correspondence with the cyclic reduced words in certain generators. And of course, I should have said, I think I said it somehow, but the cyclic reduced words, of course, I have to choose a surface word beforehand. And then, we have our nice isomorphism. And then we have these three things. The cyclic reduced words, also, my surfaces are all negative Euler characteristics, so I can endow each of them with a metric of constant negative curvature, and then there's a geodesic in each free homotopy class. So I have these three objects that they are, in some very vague sense, the same. And I'm going to now look at numbers associated with each free homotopy class. One number is the self-intersection number, which is the smallest number of crosses that an element in the class has. And for me, when I say crosses, I always think two branches coming together. If you have three, you just wiggle a little, and you can't properly. Three branches coming together, for me, are three self-intersection points. So, as I said, we have an integer associated to each free homotopy class. The word length, which is the number of letters of the word associated to the class. And, of course, the word length depends on our surface word or the choice of the generators of the fundamental group of the surface. And if we have a metric, we also have the length of the geodesic in that class. Any question? OK, everybody, I'm going to take a quiz. No.
Yeah, no, I want to know one thing. You allow any word with just a restriction that you would not have a small capital of the same?
Yes.
That's the only restriction.
Right.
You could even have also things like AB, I mean, things like factorizing in the product of the two same words.
A to the n, B to the n. Yeah, sure. Not, yeah. Or powers. A, B to the n, A, B all to the n, that's it.
Thinking about this Linden word. Linden words. Wait. No, that's matter.
Sure.
Yes.
OK, so, in most cases, each of these numbers can be computed with this computer. Dennis is waving. Yeah, they're cyclic. Oh, maybe. OK, so now, well, we already defined intersection. So now let's look at a more complicated curve than the one A, B, and B that we had before. So this one is here in the torus in purple. And you see a little bit the purpose of cutting up our surface, because now we can look at our curve. These two are the same. Here is in the cut up version of the torus with one boundary component. And this is the curve word associated to this particular curve. And I wrote it, you see, often I'm going to write them linearly again, because it's very painful to write a ring of letters. But in your mind, you should see a ring of letters. And now I'm going to look at the intersections. I try to study the self-intersections the self-intersection points of this curve. So here we are. I look, let me just go one back. You see here, I'm going to look at this point, which probably you can see it is light blue. And I wonder why that point is there. What causes that point to be there, to be an intersection point of the curve? This point is in this piece here of the curve that goes from the segment, the edge labeled by small b, to the edge labeled by capital B, and it goes in this segment, which goes from the capital A to the small a. So when I'm going to have two pieces of curve like that, well, to have a piece of curve like that, my curve has to come here, enter into the capital B, and then this piece is glued here, and then go to the capital B again. So my word has to have a capital B and then another capital B right after. So there it is. Same idea, to have a piece of curve running between the two vertical edges, I have to have a small a, small a. And in this case, I have two occurrences of two consecutive lowercase a's. Well, this one corresponds, let's see, I go here, come here. So this one corresponds to the first one, this one. But now this really doesn't depend on. I didn't understand that. I couldn't see the light. So what I'm saying is this segment here, where is it? Well, it comes from here. It comes from first I go to A, I come from B, go to A, so it corresponds to this two-letter subword. This A, this A. Okay? And but every time I can have a word of 2 million letters. If I have an AA and a BB, I'm going to have a crossing. In fact, each occurrence of such a pair gives me a crossing. And if you're going to remember something, this is a good thing to remember. Unfortunately, the things are a little more twisted, and to look at all the intersection points, we have to see a little more delicate points, but the essence is there, AA, BB. So let me just tell you, so here they are, and here they are marked. Now, here there's another intersection point in red. Let's see, it's here. No, it's in red. Let me see, 1 second. It should be this, I think. The color is confusing me, but, well, this point here, for instance, yeah, this point here, well, it goes, both pieces of curve are born in the same edge. So a priori, if I look at the words, I don't know whether there's an intersection or not, because they could do like this, or they could do like this. So to know whether there is, I have to go to the past. So I look at these 2 points here, which correspond to this, and they come from different edges. And what we do is we open it up. So this is the past. And what you see here, the example that we had before is we have two pieces of curve are born, one here. They go to the same edge. And then, in fact, in general, they can go together, crossing the same edges for many, 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 many fundamental domains. And at the very end, at any time they can cross, but what is important, the words only tell me start here and go parallel. I don't know whether they cross or not. But what I know is at the very end, either I do this and I have a crossing, or I do this and I don't have a crossing. So the whole intersection depends on the beginning at the end. The middle is the same. So if I look at the beginning at the end, in fact, I have that laptop there, hey, look at the beginning at the end, I give you the proper instructions, and it tells me, yes, there's an intersection or not. And you can have, also the same thing I described with the curves going in opposite directions. One goes like this. But it is important that who cross, because be in opposite direction. Questions? Yeah, you're going to be tested at the end, so. Anyway, so this really counts the intersections now. So there's a one, if you give me a representative of the curve that intersects in the smallest number possible of points, double points, then there's a one, this is alpha, the representative, then there's a one-to-one correspondence between the intersection points and pairs of certain subwords of my original word. Which pairs? Well, the surface word tells you which pairs are going to give you an intersection. So you look at the surface word, and you do a little, thinking, and you get that. In particular, so each intersection point is labeled by a pair of subwords, but that's too much information. If you want to know the self-intersection number, you just count how many you have.
You have to think of the word as cyclic, right? You go around and around.
Yes, but everybody else remember the word is cyclic. Sorry, I'm teasing. We are married, so. Okay, so now this is an algorithm that can be programmed, and I program it. And this is really just playing with the computer. What I did is I made this table. So the table was a counting. So I was looking at all words. And now I asked the word to be cyclic, reduce, and oops. Oh, okay. Something happened? No? And in this column, in the column, say number 1, I'm going to put words that when I compute the self-intersection of the corresponding curve, I get 1. And in the row 2, it means 2 letters. So for instance, here I have words of 2 letters whose self-intersection number is 1 in the punctured torus, this particular surface word associated to the punctured torus. So here is, the first pieces of the counting. So for instance, what are the words of 1 letter? Well, they are A, B, capital A and capital B, and they don't cross each other, so they're all self-intersection 0. And I should have said, because now you can ask me, so AA is not here, so I'm asking also the words are non-power. So now I'm going to remove the non-power words. So A to the N out, or AB to the N out. And you can ask, I can tell you why. You lose symmetry, there are less patterns. It's not the right thing to do in this case. Is this clear? Okay, so then I keep counting. So this is the table, a little more. And here is more of the table. I already have to chop it, and more. But this is just to show you that you really have to take non-powers. If you consider powers, you get these islands of 0. The pattern is broken. So that's one sign of the mathematical God that non-powers should be considered. So this is it. And here it is, bigger, for you to admire the beauty of the patterns. This is like, so here, these pictures are the same in the sense that in every little square that I get 0, I put a black, I paint it black, and then the colors where you have curves. So these are, for instance, the ones of word length 20 letters, and the darker the color is, the more curves one has. So anybody sees any pattern here that want to describe? Or any guess? Huh?
An exponential?
What's that?
An exponential?
An exponential?
I mean, it looks like
The curve?
Yeah.
Yeah, it's very hard to see. The curve, in fact, and if you do it, it's a parabola. It's a little flat here. You see this flatness? But, it's discrete. It's really, really hard to see. And this is a parabola on the nose. And I talk, if you invite me next year, about it. But this is really almost a, parabola. But, yeah, well, there's also the zeros are on one side. The non-zeros are on the other side. And you see also that, well, especially in the last row, it shows, that, well, here I have very few, and they grow a lot, and then less. By rows seems to be, the curves of a certain self-intersection accumulate in the middle if you fix the word length. So now this is the row 8 of that table, meaning these are all the free homotopy classes represented with words, cyclic reduced words of 8 letters, and how many we have with each self-intersection. And we're going to draw an histogram, so we're going to put rectangles which are proportional to how many curves I have in each of the cells. So this is it. So, the middle, you see, seems to be higher. Okay, so this is now, should have done with more suspense, but here is now the histograms with more and more word length. So you see what happened. This is word length 4, 6, 8, and this is 20. See any pattern? No. So, I jumped really high when I saw this. And I was reading a paper of Steve Lally, who's a probabilist in the University of Chicago, and I sent an email. He was studying this type of problems, but instead of looking at word length, he was looking at geometric length, like with constant negative curvature, the hyperbolic metric. And I said, look, I think the distribution of self-intersection, sampling by word length is a Gaussian. And he said, no, I don't think so. So I just sent the picture, that picture with no words, and he said, let's prove it. And we did. And we did. So here is the theorem. And the theorem says that, well, if you look at, this is of course, asymptotic. If you look at all the free homotopy classes of a large word length, then the distribution of the distribution of these classes by self-intersection is a Gaussian, or it gets very close to a Gaussian, and the mean is a constant, this constant times the word length square, and the variance is these more complicated constants times, they say, the variance L squared 2. So here it is. And then my probability is not, fantastic, but I started to look at a book, a notebook of probability, and they're studying this problem. You have a disk, and you're going to throw n sticks, and you think that there's a uniform probability of landing in each pair of boundaries for the sticks. What is the expected value of the intersections of these sticks? Well, it turns out that is n times n minus 1 over 6. N is the number of sticks. So this is, asymptotically the same as self-intercept when your Euler characteristic goes to minus infinity. So your surface is, almost like a disk that you just glue in some way. You get also L squared over 6 self-intersections. The same was like in a circumference, and that was nice. But then the variance of this here is nq as approximately nq divided by 45, which again with the Euler characteristic was minus infinity. This is it. So it behaves like just throwing sticks on a disk in the very limit. So when am I finishing? 1:5?
Yeah, 20 maybe, yeah.
Wow, okay. Ooh, okay. Well, we have a joint student with Dennis who proved this result for closed surfaces. And let me skip. Let me just skip faster. Oh, seems to be a little frozen. Oh, I have to, because I was, in fact, another experiment. So this I did, I think, maybe with one of the youngest person in the university and one of the older person in the university a few years ago. Bernie Maskey was an emeritus professor, and, Karen Lee was an undergraduate. And what we did was just take all the words, again, we fixed a surface, in this case was a pair of pants, and take all the free homotopy classes of a certain word length, and to each of them compute the length. And then see how this length distributes. So instead of studying distribution of self-intersection, we study distribution of geometric length. And of course, this is different for different metrics. And here I have 4 example metrics. This is like when all the boundary components of our pair of pants are 1, 1, 1. This is when 1 is 10, the other boundary component is 0.1, and the other is 1, and so on. But despite these gaps, that the things that maybe looks a little weird. This is like, are you converting really to a Gaussian? But the gaps are really related to this big difference between 10 and 0.1. And when you really push the limit, there are multiples of 10. They are going to disappear. So we conjecture that this happens always. And in fact, at some point I did try to prove, and I looked at Hilal papers with matrices and products, but I went nowhere, and something else happened and didn't prove it. And then a few years ago, somebody sent me this paper where they did work in that, it was proven by Gaiman, Taylor, and Tiozzo in a more general setting that the distribution of length goes to a Gaussian, and they even made it more general. It works there's a central limit theory now for many hyperbolic manifolds in a wide variety of cases, that the little conjecture we have, distribution of length sampled by pore length is a Gaussian. So that's good news. So since this is a Lie, Lie what? Huh? Lie-Størmer colloquium, I'm going to talk about a Lie algebra.
Question, did they use the first-order random matrix product here?
I don't know. I should check. Not in the first iteration, as far as I know. So I'm going to now give you, this is like if you're lost, you can come back, I hope. This is a present. It's a wonderful Lie algebra of curves. So now we're going to have a surface which has an orientation, and it can have boundary or not. And we're going to look at, we're going to be looking at, again, the free homotopy classes of curves on that surface, directed closed curves, as before. And here I point out, like we know very well the fundamental group, but the free homotopy classes is a set. And we're going to take linear combinations of elements in that set. Formal linear combinations, so we all tend to think that the -1 of an element is minus the element. No, these are 2 different elements. Just formal linear combinations.
Could you say again what the free homotopy classes is in the set?
Say it again? For free homotopy classes of closed directed curves on a surface.
Say what that means. He wants to know what free homotopy
Oh,
classes
so I'm looking at closed directed curves on a surface up to continuous deformation.
And then you pick one representative, or what?
No. And then I choose each class. The class is my object. I'm going to pick a representative in a second, but yeah.
Free, you expect, what is the free?
Free means is as opposed to base homotopy class. People, when we say homotopy, people think, I'm in the fundamental group, and I want to take you out of that idea. So here is my definition. So we are going to take linear combinations, and the coefficients, you can choose your favorite field. Well, let's say z here, z, the integers. So I'm going to define a bilinear map. And the bilinear map is defined by take 2 classes. I'm going to define it in any pair of elements of the basis. So take 2 classes and choose one representative of each class. Choose it. Choose it in such a way that they intersect transversal double points. So here I should have my representative, one and the other. And in this example, they intersect in these 2 points, one green and one purple. So now I'm going to, each intersection point is going to give me a term of the output of this bracket. So a term consists in a free homotopy class and a certain coefficient. So we're going to look at here the green point. So the green point, here is going to give me this free homotopy class. If you see here what I did, at this point I did a small surgery, which is just the old loop product. You go at the green point, I go, first around the light blue curve, come back, and then go around the dark blue curve, come back, and this defines a new curve. I take the free homotopy class of that. That's, the free homotopy class of that term, and I put a sign comparing the orientation of the surface with the orientation defined by, these two oriented tangents of the two curves there.
You decide how to put the little green pieces by following the arrows?
Yes.
Going up.
Yes, I just, as I said, because I said, you go around one curve following the direction and go around the other curve following the direction, and that gives you this little surgery, respecting the arrows. So we do the same with the other one. In this case, we get another curve, and then we can extend by linearity. So this is the moment. This magic thing combines, these two operations we know well. We're intersecting the curve, so this is intersection product and the loop product. They are merged together. And what is the question here? Not Dennis, everybody else. So, huh? Huh?
The question is, why is this silly algebra?
But first, remember I said choose two representatives. So I have to prove that it's well defined, and yes, and then once it's well defined, we have to check it's a Lie algebra. Because this is done by choosing two representatives. I had to show that every pair of representatives should give me the same. So first, this is well defined, and the way to see it is, so here I have an example. Here I have I'm going to have a homotopy between pairs of curves. So this is one pair, and this is another pair, and I continually deform both curves along this black path. And we're going to deform it, and the change will be only in little disks, from looking, say, something like this to something like this, or this and this, or this. These are the type of changes that can happen. So, of course, not all ways of deforming our curves are like that. But using transversality, I know that there exists a way of deforming these curves that, you can have much more pathological things, but I can just, cross them and get a tangency from here between this and this, just in a very short second. And then you check, well, here I should see, the arrows, put all the possible arrows for this case, and see that, say the two arrows point up, the blue and the red. Well, when you do the little surgery, the term corresponding to this and the term corresponding to this are the curves, the class of curves is the same, and the sign is opposite. So then these two are going to cancel. So when I compute the bracket at this point, I'm going to get the same bracket at this point. And the same type of things happen, along the black curve. So there's the bracket is well defined. And I don't have I have to tell you what is, no, I have to find it. Sorry, I don't have the proof that is, I think I need a good picture, the proof that is a Lie algebra. This is terrible. I just remember I was going to put it, and I didn't, but I might be able to find it. Easy. Light table. No. Well, maybe I have to wave my hands. Pictures are so much better. Which one is this? Nope. Okay. Let me just go to the other one, and where was here? I wave hands. So let's prove, this is skew symmetric on the nose, because I put the sign by looking at the order of the two, order tangents, compared to the orientation of the surface. Now let's prove the Jacobi identity. So you have you are bracketing these two curves. What is the bracket of these two curves? Is the sum over the intersection points of these two curves of certain terms. These terms, remember we look at them as you go to the intersection point, go around one curve, and then when you go back, you go around one curve completely, go back to the intersection point, and then you turn, you think you're a little car, and you go around the other curve. So now we have two things. Let's bracket it with a third thing. So if this curve is red and this is blue and the last one is green, so my green curve, the last one I'm bracketing with, either will intersect a red piece or a blue piece. So it will give you like two type of curves, where in the first one, the red and blue, so I start with the red, and maybe I'm going to arrive to an intersection of the red with the green. So now I have to turn at the green and go around, and then do the red, and then I go back and I do the blue. So here is intersections of red and blue, red and green. One type. The other will be intersections of red and blue, blue and green. So these are the two types. So these are pairs of intersections now, and these are pair of intersections. So this is when I do the bracket red, blue, and then I bracket this with the green. Now I'm going to go and do the bracket of blue, green, and bracket this with the red. And I'm going to do the same thing. I'm going to get two things. But if you see the structure of my thing, I'm going to have, when I do red and blue, red and green, the first one, sorry, this really needs a picture, I'm terrible, but, well, red and blue means you can't think the red is the one used twice. And I'm going to have six things when I do the three possibilities, the three cyclic permutations of A, B, and C. And there are 6 things, but the red in the center is going to appear twice, and they're going to cancel. When the red is in the center, it means that they're the same pairs. Again, this is the sum of pairs. And if you're not convinced, and probably you shouldn't because this was not a great proof, well, see me during the dinner and I'll draw you a picture. So let's see. And I'm going to skip this. Oh, no, this not. So here is one thing. And now I'm almost done. Sorry. OK. One more thing, like to connect with the previous part. So remember I told you that we have this word, and subwords tell you the self-intersection. In fact, it's not hard to see that also they give you intersection, the same type of arguments. So then, since the bracket, this Goldman-Lee bracket, is a sum over intersection points, well, it's defined into this ring of letters. And in fact, these pairs of subwords that determine intersection tells you ways of cutting your curve. So if I have a certain pair of subwords, which is like an intersection point, it tells you, well, cut your word here and here. So I have these rings of letters, and I'm going to cut them open. They are oriented rings of letters. They have an arrow, so then I'm going to attach them. And I get this way a new ring of letters. I may have cancellation there. That's fine. Then I cancel, and I get a new rings of letters. And I can also get a sign. So really, this allows you to put this Lie algebra also in a computer. And in fact, Dennis mentioned this in his talk yesterday, 2 days ago. No. The Abel talk. And we were trying to prove certain things about this Lie algebra and extend the structure, the Goldman to arrive Lie algebra, and we were trying to prove something, in fact, that it was false. We didn't prove it because we're very smart. But I found finally a counterexample. I mean, the computer found a counterexample after I ran it. So the thing we were trying to prove is not true. And that's a little longer to tell, but maybe I'll tell you one thing that was, and I can finish with that. Don't get scared. Because one thing I did is counting, sorry. Oh, it's here. So I was reading Goldman's paper. He found this bracket by studying representations of the fundamental group of a surface into Lie groups. It's a wonderful paper, full of mathematical juice. But at some point, he says he's proving a lemma, and he says, then he's trying to compute the bracket of two curves, alpha, a curve alpha and alpha with the opposite direction. And he puts this picture, and he wave hands and says, and it's clear from the picture that the bracket is 0. And I was trying to deduce that the bracket is 0, and it was not working. And well, finally, I put it in the computer, and it's not only not working, it was never 0. It was very much not 0. What happened is that if you have a curve, and the inverse curve, and I have a picture of a generic example here. So this is, this is just a figure 8 curve, but this is what happens. We put a curve and the same curve in the opposite direction. You see they intersect twice, the red and the blue. In general, a curve and the curve in the opposite direction, they're going to intersect twice the self-intersection number of the original curve. Well, the bracket, never had cancellation. Sometimes there is cancellation in the bracket, but they never has a cancellation. The number of terms was 2 times, the self-intersection number exactly. So, anyway, so this is, in fact, I made a conjecture that this is equal, and this was proven recently that it's exactly twice. It was just out of the oven, this paper. And they prove it that if the bracket of x and x bar is 0, then the curve is simple. But I want to one day prove the conjecture that I have. OK, I'm done, probably over time.